Let's now take an example and answer the question of what is the order of the visit of the nodes and also the path returned by BFS, DFS, and UCS. So the goal here is to go from the node S start to the node goal, right? So we're going to see with different strategy how it works. Let's now take an example to practice. So this example is we have this graph and we want to search the path from S to G. So we have the start node and the goal node. And you want to know what's the order of visits of the nodes and the path returned by BFS, DFS, and UCS. So first of all, let's consider BFS. So for BFS, remember that the data structures to keep the elements or the nodes in the fringe or the frontier is a queue. So we're going to enqueue elements and dequeue elements as we visit and go through the nodes in the tree. So I'm going to enqueue from this side in this example and dequeue from this side. So let's start with BFS. So remember for BFS, we have a queue and we can put the element in the queue to be explored. So I'm going to enqueue from this side and dequeue from this side. So the first element is S, so we start with S. From S, I'm going to add the elements, the children of S, A, B, C, into the queue. So the next step is to enqueue A, B, C in this order, in the lexicographic order. S is now visited because we have already explored and added its children in the queue. So S will become in the list of order of visit. It's highlighted here in red so as to see that it left the queue. All right, the next element to explore is A. So when we explore A, we're going to add A children, and the A has only D as children. So we're going to add D. Afterwards, after D, the next element to explore is B. So we're going to take B, dequeue B from the queue. The B has D, G, and E. So D and E are already in the fringe. We're going to add G. The next element to explore is C. C has as elements E, right? But E is already in the fringe. We do nothing. Then we dequeue D. D has element as children F. So we're going to add F to the list. Then we dequeue the next one, which is E. E has H. We're going to add H. Then from the next element is G. So we dequeue G. And we found out that this is the goal that we want to achieve. So the final path is the shallowest path, which would be S, B, and G that lead from the start to the goal. And the order of visit is S, A, B, C, D, E, and G. This is the status of the queue at the end. F and H were not dequeued because G has already been found. Now, how about DFS? So we know that DFS, depth first search, goes all the way in depth. So we're going to really explore one full path before going to the next one. So initially, we are going to use a stack to store all the fringe elements in the fringe. So initially, we start the stack with the main element S, or the start element. So that's going to be the node is being pushed in the stack, and anything we pop also from this side. So the next step is once we push S, that's going to be the only element in the stack, so I'm going to pop it first. So I'm going to pop S and add S in the order of visit. The next step is to, once we pop S, we're going to add S, and then we are going to add S children, A, B, C, in the, push them in the stack, but push them in reverse lexical order, and the reason is to be able to pop them out in a lexicographic order. So I'm going to push C, then B, then A, and the next element to pop would be A. Once we pop A, so I'm going to add it to the order of visit. A has D as child, so I'm going to push D inside, and then the next element to explore would be D. D has F, so I'm going to push F inside, and the next element to explore is F. Then after F, F has E and G as children, so I'm going to put them again in reverse lexicographic order. So I'm going to put first G and then E. The next element to explore is E, and E would have as children H and F, so F is already explored, so I'm going to add into the fringe the element H. The next element to explore is H, and H has as children only G. And we find the goal, so the process will stop. So technically the order of visit would be S, A, D, F, E, H, G, which corresponds to the path, the the deepest path going through S, then A, and expand by D, and then expand by F, and then expand by, by G. Right? So this is the deepest path in the search to reach the goal from the start S. So how about DFS, depth first search? So remember, depth first search would explore a full path. We use a stack to represent or to put the nodes that are in the fringe or in the frontier. So the stack will, we assume in this case that we are going to push them in this way and pop them from this way. So push, we add an element in the stack in this direction, and we pop or extract and explore the elements out in this direction. The first step, once we pop S, we're going to add S children to the stack. So we're going to push the elements A, B, C in the stack, but we're going to do that in a reverse lexicographic order. And the main reason is that we want to pop them out in lexicographic order. So we're going to push them as C, B, A, and we're going to pop them out as A, B, C. That's the trick. All right, so the next element to pop now is A. So A has D as a child. So we're going to add push D in the stack. Afterwards, so A is considered as visited. The next element to pop is D. D has F as a child. B has already been added earlier. Okay, so remember we checked that it wasn't already visited or explored. Then the next element to pop is F. F has two children, G and E. We put them again in reverse lexicographic order. So it's going to be, we are going to push G, then push E. And the next step is to explore to pop the E. The E popped will bring its child H. So we're going to add H to push the H in the stack. Then the next element is to pop H. Once we pop H, H will have as children G and E, but they are already actually in the list or explored. So we are going to then, since H now is explored, E is explored, we are going to pop the G, which turned out actually to be the goal, and we are done with the process. The full path that's going all the way down to the goal is S, A, D, F, and G. But the nodes that were explored are these nodes here. All right. So now, how about UCS? So how about UCS? In UCS, we have a kind of BFS, but the priority is going by cost, not by depth. So initially, we're going to put S, the start element, into the priority queue. So remember, we are going to have a priority in which each element is annotated by the cost to that element. So initially, we have to spend $0 or 0 kilometers to reach S. So S would be annotated with 0. Okay. So I'm going to enqueue from this and dequeue from this. All right, the next step is to dequeue S0. So I'm going to dequeue S0 and add its children. So the next step is to add the elements A, B, and C. A has a cost of 3, B has a cost of 6, C has a cost of 2. So I'm going to put them in the increasing order of cost. The next element to dequeue is C2. C2 will add the element E3. And it will squeeze it between A3 and B6 because it has a lower cost than B6. Right? So C2 has as an element now has is dequeued. It's added to the order visit. The next element to dequeue is A3. A3 has a path of 3 to D, right? So we're going to add D6 to the list. Now we dequeue E. So once we dequeue E, we realize that actually to reach B, we have another path, which is 2 plus 1 plus 2, which is 5. So we can update the path to go to B. Initially, it was 6 going from S. Now it's 5 going from this path here. Okay. So now we have to dequeue the next element. The next element is B, B5. So once we dequeue B5, we add the missing elements from those who are already in the queue. We don't add them. Those who need to update, we decrease their cost, etc. Okay, so then we dequeue D6. D6 will add whatever was not there already. And then we explore H8. H8 has as children G. G was already there, and we don't have a better choice than G14. And then we dequeue F9. F9 has also another child, which is has a child which is G. We don't also change it because to go through F9 we have a larger cost here. So now we dequeue G14. Once we decode G14, we are reaching our goal, and the path would be actually the shortest path or the lowest cost path, which would be S, C, E, B, and then G. So this will be 2 plus 1 plus 2 plus 9, which will be actually 14.